Hi everyone, Mr. Martella here with Tsunamis Part 2. If you remember, in our last video, we talked about what a megathrust earthquake is, how this happens at these reverse faults, at these subduction zones, usually oceanic, continental subduction zones, parts of the world where we've got an oceanic plate being pulled beneath a plate that is carrying continental crust. And these are the earthquakes on this planet that are the largest. They generate the most destruction. And if they are submarine, which most of them are, they can cause big tsunamis. Okay. And we defined a tsunami as a series of water waves that can inundate an area. And we defined it as, the cause of tsunamis as either submarine earthquakes, volcanic eruptions, or landslides. Okay. So today what we're going to do is we're going to take the idea of the four stages of tsunami life, which were initiation, split, amplification, and run-up, and we're going to apply them to two of the most destructive, most powerful earthquake and tsunami events that we have ever recorded on this planet. And we're going to start on December 26th, 2004, which is referred to as Boxing Day in this part of the world, Sumatra, Indonesia. Now, if you're not familiar with Indonesia, here I have a picture for you. I have the upper island of Indonesia in a big circle here because this island is called Sumatra. The lower island down here is Java. All right. Now we're going to come back to this part of the world in a few weeks as we study volcanoes. Krakatoa and also Toba are two volcanoes that have had sort of like mega blasts in the past. So we're going to talk more about the geology and the tectonics in this region as we move on. But for today, let's talk about what happened on December 26th of 2004 in Sumatra. First, this is a screenshot from Google Earth, and what you see here is the upper island of Indonesia, Sumatra, all right? And you notice this big feature down here under the ocean, all right? That is a deep ocean trench, all right? So there's the outline of the trench itself, and this trench in the upper portions, in the northern parts of the trench, it's referred to as the Sunda Trench. If I would show you down lower, further south, it's referred to more as the Java Trench. Okay? So this is the area that we're going to focus on today. Now, when the earthquake happened there, it happened in a really complicated setting. All right. Now, we've taken a look at faults and, we talked about three fault types: the strike slip fault, the reverse fault, and the normal fault. All right. We associated strike slip faults with transform boundaries and faults like the San Andreas, which caused the 1906 Great San Francisco earthquake. We've also looked at the Aleutian Trench, all right, which is a reverse fault. It is a convergent boundary, and it is another sort of megathrust type area. And that's the fault that was responsible for generating the second largest earthquake in history, the 9.2 Great Alaskan earthquake. So, we've talked about them in very simple terms here for our purposes in 8th grade. But I want you to realize, as you look at these two images, that the faults in this part of the world are a lot more complicated than what we're learning. All right. So, I won't require, my 8th graders to to remember much of this other than the fact that it's pretty complicated, all right? So we have a couple of things going on here. We've got oblique thrust faulting, and we've got a decoupled fault, all right, where we've got pure thrust faulting, where we've got this sort of reverse faulting action happening with, you see here, forces that are pushing the blocks of rock at the fault together, all right? And the block of rock here in the middle being thrust up, all right? So this is the situation that we're dealing with. There are also strike-slip faults in the area, okay, which are common more around divergent boundaries. But this shows the decoupled structure, all right? Letter B here on the bottom shows the decoupled structure of the fault at the Sunda Trench. So it's pretty complicated. There are a lot of things going on under the ocean in that area. This shows the displacement of the rock at different points around the fault at the trench. Excuse me. So you can see a couple of things here. By the way, I know that my camera is covering it up, but these images and this information for this presentation comes mostly from the USGS. So here what you see is how the rock moved at different points around the fault. And what we can see here, all right, let's identify first, here's the subducting oceanic plate. That's what's being pulled back into the earth. Here's the overriding continental plate, which has the coastline. All right, so this would be the fault plane in this area here. And you see all these arrows pointing up, pointing over, some pointing down in different directions. Remember, earthquake energy is going to travel 360 degrees from its source. So we're looking at a lot of two-dimensional sort of images here, but remember, we have to keep in mind this is happening in a three-dimensional world, okay? Like when we define tsunamis and the split stage, we talked about the distant tsunami that heads towards the open sea and the local tsunami that heads towards the shore. But remember, it's not just two directions, okay? These waves are moving out 180 degrees from the point of origin of the earthquake, the seismic waves and the water waves, okay? Up here in the left-hand corner, you see a focal mechanism, all right? It's affectionately called a beach ball in the seismic community. And I mean, we could spend a whole 40 minutes dissecting how seismologists come up with these focal mechanisms. For our purposes here, I just want you to realize that these focal mechanisms are generated for every earthquake that the USGS reports. And what they indicate are the direction of slip and the orientation of fault in which it occurs. So, the black is compression, the white signals dilation, waves that are moving towards and away. This has a lot to do with primary waves and when they arrive at certain areas. But for, just to make it as simple as possible, imagine this is the fault plane here, okay? And you've got, one plate being pulled underneath another, all right? So this shows the angle, the orientation of the fault, all right? So the direction of the slip here obviously is shown a lot better in these arrows. So we're not going to dig too far into the focal mechanisms, but, just remember that Mr. Martella told you a little bit about the beach ball if it ever comes up again, okay? So a lot of complicated things going on here in Indonesia, in the Java Trench, the Sunda Trench. What exactly does all this mean? How did this tsunami propagate? What did it destroy? What was the destruction? Well, the National Oceanic and Atmospheric Association, the NOAA, has some really neat tsunami simulation models. And I've got a couple of them here. The first one, if you take a look at it, what this represents here is the ocean floor, all right, with all the water above drained away, all right? So here you see, this is the northwestern portion of the island of Sumatra, All right. And what we're going to watch here is how long it took the seafloor to displace or to move after the rupture, the initial earthquake. So what you're going to see here, we're going to end up with 750 miles of a ruptured fault line under the sea. That's the length of California. All right. So I'm just going to play the animation once, and then I'll play it a second time and talk a little bit more about it. All right. The first thing that I want you to sort of key in on as you're watching this animation, everything that turns red is going to be, remember, with tsunamis in initiation, the initiation stage, you have uplifting and you have down dropping, all right, of the crust in certain areas. So for this earthquake, you're going to see everything in red is going to be the uplifting of the crust. Everything in purple is going to be down dropping of the crust. Okay. And you're going to see how earthquakes literally tear through faults. Watch. So there, the earthquake has begun, and it's moving at 2.5 kilometers per second. All right. Over a mile per second, all the way to the north. And you're seeing the continued uplift over there. All right. So let's watch this one more time. Remember, 2.5 kilometers per second. All right. So if you say 3 kilometers per second, that's about 2 miles per second. All right. That this tear or this earthquake happened. So let's watch again. Here we see the uplifting on the outside, the down dropping on the inside as the fault ruptures from south to north. And even once it hits the northernmost parts, you still see more uplifting on this side, okay? So that is how the fault essentially tore as the earthquake energy moved from the focus or the hypocenter or the epicenter northward, all right? Excuse me, at lightning fast speeds once again. Now, this model is going to show, now we're going to put the water back on top of it, of the ocean floor. Okay, and we're going to see how the water was affected. And this is going to take us up to 6 minutes after the initial earthquake. All right, so remember the uplift in the last animation, the uplift occurred out here. The down drop occurred down in this area. So let's see how that affected the oceans as this event transpired. There you go, 200 meters per second. And you see the tear, the down dropping. You see over here the distant tsunami, over here the local tsunami. And you see the waves, how high they were as they hit the main island over here, and the wave working back this way, absolutely huge once again. All right. So let's take one more look at this. And I will post both of these simulations separate from this presentation on our Schoology page so that you, my students, can check these out for yourselves. Let's watch this one more time. You just don't get to see tsunamis modeled this way all the time. Let's watch it. So the earthquake is going to begin. Boom. You see the fault tearing, the land uplifting, land down dropping, local tsunami heading this way, distant tsunami speeding off into the deep ocean. And look at the gigantic sets of waves that are crashing into Sumatra right here, Indonesia, and the waves moving behind Sumatra in the distance there, and all the perturbation of the ocean in between. Okay, so this is what tsunamis do. All right, and they do it very quickly. One more brief animation here. This is the tsunami forecast model that the National Oceanic and Atmospheric Association sent out. And you're going to see the areas in red were hit the hardest here. Okay, and you'll see once again how this tsunami propagated or moved. Remember, it's going to start right here, all right, by Sumatra, and this energy from this tsunami is going to travel all the way out completely through the Indian Ocean and even into the Atlantic. So let's take a look here at the tsunami forecast model for this event. I guess I should mention that this was a magnitude 9.1, so it was no small quake. So coastal run-up forecast points. So here we're looking at where the tsunami would have affected things the most. Anything in red is going to be one of the harder hit areas by the tsunami. And if you look here, 3 hours, 4 hours, it shows you the elapsed time, how fast this travels. It took about 7 hours to hit the eastern coast, the Horn of Africa, and look at the damage that it did there. Now you see the waves continuing, and they're moving around the southern tip of Africa and into the Atlantic Ocean. And look at all of the reflection, the bouncing, and the sheer anger in the water of the Indian Ocean. And, you know, this was the 2004 Boxing Day tsunami. And you can see here, this is modeled over a 24-hour period, all right? And you can see how the energy or the wave amplitude here, which is the height of the wave, continued out into the open Indian Ocean and affected just about everything in that area, including Australia, all right, Southern Africa, Eastern Africa. A bunch of people were killed in India, all right, but most of the deaths occurred right here in Indonesia. So the 2004 Indonesia earthquake and tsunami fact sheet. The earthquake was a magnitude 9.1. It was a shallow earthquake. It was only 6 miles deep. It brought with it 3 to 5 minutes of shaking, depending on how close you were to the fault and to the epicenter. It released an energy amount equivalent to 475 megatons, or 23,000 nuclear bombs that we dropped on Nagasaki. 23,000. Ended up with 750 miles of ruptured fault line. The rock along the fault moved 60 feet in some areas, 60 feet in some areas. And wave heights ranged from 50 to 100 feet. 100 feet is about the height of a 10-story building. Okay. The tsunami hit on average 15 minutes after the earthquake. Some people in Sumatra had much less time than that to react. And the saddest statistic on the fact sheet here is the last one. This event killed 225,000 people. It was the deadliest natural disaster in recorded history. Right? So that is Indonesia in December of 2004. In the next video, in our next class, we will discuss the March 11th, 2011, I believe. Yes, 2011. I just want to make sure I said that right. Earthquake and tsunami in Tohoku-oki, Honshu, Japan. All right? See you guys in the next video.